Okay, welcome everybody to the sixth Fall 2009 Nokia Distinguished Lecture on Cyber-Physical Systems, which is organized this semester by CITRIS, the Center for Information Technology and Research in the Interest of Society, and CCIT, the California Center for Innovative Transportation. My name is Alex Bine. I'm an assistant professor in systems engineering over in the CE department, and I'm the host of these lectures. This lecture is specifically organized by the Intelligent Infrastructure Cluster at CITRIS. It's currently broadcasted live to the three other CITRIS campuses, Merced, Davis, and Santa Cruz. And for the viewers who are watching us online, you can IM us your questions, which will be read to the speaker at the end of the lecture. So let me say a couple of words about the Nokia Distinguished Lectures on Cyber-Physical Systems. These lectures are sponsored by Nokia, and they're specifically focused on projects which model systems which ally physical processes and computational processes. And over the last couple of weeks, we have had a lot of different such projects to do with water monitoring systems, with multiple agents moving and coordinating motion. And I think this week we're going to have a very good example in the civil engineering domain with large-scale infrastructure systems. Let me also say that the program of the Cyber-Physical Lectures is available on the web. You can look at this on our website at traffic.berkeley.edu. Before I introduce this week's speaker, let me announce next week's speaker. We'll have Professor Naomi Leonard from Princeton. It's going to be on November 4th, same location, same time, and she will talk about fleets and flux, collective motion and sensing networks in nature and robotics, again in the area of cyber-physical systems. So today, it's my pleasure to introduce our speaker, Professor Bill Spencer from UIUC, who will speak about smart sensing technology, a new paradigm for structural health monitoring. And I'm going to introduce Bill shortly. So Bill got his PhD from UIUC in 1985 in theoretical and applied mechanics. And he's currently the Nathan and Ann Newmark Endowed Chair in Civil Engineering and the director of the Newmark Structural Engineering Laboratory. So he is a fellow of the ASCE, an elected foreign member of the Polish Academy of Sciences, and he's the North American editor-in-chief of Smart Structures and Systems. So please join me in welcoming Professor Bill Spencer for the talk.
Thank you, Alex. It's my pleasure to be here and tell you about some of the work that we've been doing. As a matter of fact, the genesis of our work was here at Berkeley. Some of the early DARPA NEST projects led to our interest in this topic and to the work that I'll be telling you about today. I need to acknowledge the National Science Foundation. Dr. Chi Lu is the program manager, as well as Intel Research, Lama Nachman, and several student fellowships from the Vodafone. So, by way of introduction, the aging infrastructure in developed countries requires cost-effective and timely inspection and maintenance. Maybe you've seen this graph here on the right. This is, in red, is the total number of structures that were constructed as a function of year. This is bridge structures. And on the black line, this is the percent that are structurally deficient. So you can see that in the 40s, 50s, and 60s, there were many new structures that were constructed. But as time goes on, these structures need to be repaired. And so we have to be worried about this classes of structures. And so the ability to detect damage at an early stage can reduce the cost and the downtime associated with the repair of critical damage. And here are some examples of these in India in 2007, in Paris in 2004, and a couple of examples in Seoul, that these structures were not known to be problematic, and all of a sudden there was a sudden collapse. In addition, we have to worry about natural disasters, earthquakes, winds, other extreme loading events, and we have to monitor these structures to ensure that the emergency facilities, evacuation routes, including the bridges and highways, are quickly assessed for safety, and that appropriate steps are taken to move the emergency vehicles along these routes. And these are just some examples from Katrina and other recent earthquakes to remind us of the problems that can be caused by such extreme loading events. Now, structural health monitoring, I got this from a friend in Shimizu Corporation, and the Japanese are very good at making these cartoon drawings that illustrate the main problems. And so for a structural health monitoring system, we generally have two situations. That is the ordinary situation, or the maintenance and operation, and then the emergency situation. And so in the ordinary situation, there'd be sensors on the structure that collect information, the structural performance that can then go to a data management server, and this can inform the owner, the designer, and the engineer. In contrast, during the emergency situation, we have the critical need for more real-time information, and so information about damage and deterioration of the situation during these extreme events can be fed into this data management system to inform the owner, administrators, or users, and to help in emergency reconnaissance. Now, as an outline of the talk that I'm going to give today, I'd like to tell you about what is the current status of structural health monitoring technology for civil engineering applications, to review a few of these. And then I'd like to point to what are some of the most promising future technologies for structural health monitoring. So why do we want to monitor infrastructure? I gave you some high-level views of this, but in particular, people monitor structures to control monitor and control the construction process as the structure is being built, to validate the structural designs and to characterize performance, develop databases, to characterize in situ loads, and to assist with building and bridge maintenance, to detect and localize damage before it reaches a critical level, thus increasing the safety to the public, to reduce the cost and downtime associated with repair of this damage, and to assist with the emergency response efforts, including building evacuation and traffic control. So let me show you a few examples of this. I collected these from colleagues around the world. This is from James Brownjohn at Sheffield University, and it's a structure that he was involved in instrumenting in Singapore. So the initial instrumentation was in 1994, and it's been monitored from 1994 to present. So the initial testing was for the construction process, the ambient vibration tests during the construction process, and then the ambient vibration tests after it was constructed during the that was monitored since 1996, originally for wind data, and then building was used as a wind and earthquake super sensor, and then dual rover GPS operation until March of 2005. So let me just show a couple examples. This is the, on the left-hand side is the height of this graph is the height of the building. Down here on the bottom axis is the number of days in the construction process. And then on the right is the period, or for each of the various modes. And you can see whenever the construction was initiated that the period was quite short, very high frequency, and as the structure got taller and taller, the period got longer until it stabilized for the various components of the structure. And so this is what one would expect to see, and this can be compared to the models of the structure to ensure that the construction process is going as expected. These are some of the sensors, force balance accelerometers in the roof and in the basement, anemometers, GPS antennas, and loggers. And here's what I meant about a super sensor. These are some aftershocks from a year 2000 event. And what we can do is from these measured responses, one can then develop enough information for local design spectrum. So you can characterize the local loading situation much more effectively than we can just from the typical approach. Here's another example. This is from my colleague Hassan Karim at the University of Notre Dame. It's in partnership with Skidmore, Owens, and Merrill in Chicago. And one of the things they're concerned about is what type of damping do real structures have? And if you're concerned about wind and you assume that there's 5% damping in a real structure, you're in a much better shape than if you assume that there's 1% damping. So if they can get a better handle on what real damping is in the structure, then they can refine their designs. This is Bill Iwan gave me this slide. This is a project that they have to monitor the Millikan Library. And I thought this was relatively interesting. You've got a fairly short building, 10 stories. And what we have here, this is the data for the first mode. And so if we just assumed that we had a shear building, which one might use for a 10-story building. So you've got a shear building. That would be this blue line. And you can see it doesn't characterize the real measured dynamic behavior of the structure. If you assume that the structure was behaving primarily in bending, that would be this yellow triangled line. And you can see that doesn't capture the full behavior. And then there's rigid body rotation, just rocking on the foundation of that structure. And it's these combined motions that were actually present in the dynamic response of the Millikan Library. So the assumptions that we would have in the construction of this building, or the design and construction of this building, can be validated and better understood with this data that's measured here. This is an example from Professor Fujino at the University of Tokyo, where building number 11, I believe it was seismically retrofitted. And so they monitored the ambient vibration before and after the seismic retrofit. And they were able to show that they could get a reduction in the RMS ambient vibration, and they concluded that that was an indication of the effectiveness of the seismic retrofit. This is also, Professor Fujino is a painter in addition to being a bridge engineer. And the Yokohama Bay Bridge is shown here from his 2004 New Year's card. And this structure, there were a number of models used in the design, and they were based on many assumptions. But it needs to be seismically retrofitted now. And there's the question of how do those initial models and the initial designs compare to the as-built structure. And so this structure has been monitored for more than 15 years through 10 earthquakes, and they identified several of the modes of the structure and found something very interesting. If you look on the left figure here, figure A, they assumed that the bridge deck and the piers slipped relative to each other. So you didn't have the piers loaded with the entire weight of the bridge deck and the superstructure whenever the earthquake occurred. But in this earthquake in '92, you can see that that slipping didn't take place. So you have the up here on the right figure, you can see that the bridge deck and the bridge piers are moving together. So the loads are much higher. And in this 1995 earthquake, you've got the left pier slipped, whereas the right pier did not. And so if you're going to design a seismic retrofit strategy for this structure, you have to understand that these types of behaviors exist so that they can be accommodated. This is the 3 bridges in Hong Kong that were constructed in the 90s. And I'll just focus on one of them, the Tsing Ma Bridge. There were 300 sensors installed on this structure. Data acquisition system, data processing and analysis system, and cabling system, $7.8 million. Now, indeed, this is not atypical that for a large bridge structure such as this, anywhere from $15,000 to $25,000 per sensor is the average cost of installation. And this is one of the early bridges. Now there's dozens of bridges in China that are signature bridges that are monitored in a similar way. And this in particular, this shows the 4 stages of monitoring of this bridge. First, the phase 1 was the freestanding tower. Phase 2 with the cable system. Phase 3, the tower, cable, and deck system. And phase 4, the completed bridge. And so it's still being monitored on a continuous basis. So these were just some examples, and to illustrate where we are with structural health monitoring for civil infrastructure. Currently, we can do real-time data collection and presentation. We can do data storage, data statistics and comparison with baselines, and then warnings of anomalies in the data. But that doesn't really fulfill the promise of structural health monitoring that we talked about previously. So some of the current challenges is that the data is overwhelming. There's reams and reams of data that's collected for some of these bridges, and nobody ever sees it. Sensors have defects and premature failures, the thermometers, optical fibers, electrical resistance strain gauges, etc. So reliability is an issue. Failure of the entire system, the data acquisition system, may go down. And then there's the idea of real-time damage identification and general safety and health assessment. So we're not there yet with regard to being able to achieve this type of performance or this type of information from structural health monitoring systems. So what I would like to do now is to tell you about some of the future directions that may address some of these challenges. So one of the things that we've realized is that damage is intrinsically a local phenomenon. If you have, this is the Akashi-Kaikyo Straits Bridge there. If you have some element that's damaged on the left side, it's a 1.9 kilometer span. And so if it's damaged somewhere near this left tower, the measurements on the right tower are not going to be providing any information about what's going on that far away. So the sensors must be in close proximity to the damage to effectively detect the damage. And for large civil structures, such as are shown here, that's going to require quite a dense array. So this is a daunting task. And one of the things that's been informing a lot of research these days is the bioinspiration. As a matter of fact, there's a new program at the National Science Foundation that Dr. Chi Lu is leading on biosensing and bioactuation. It's in the Emerging Frontiers for Research and Innovation program this year. And so if we look at the sensory system of the human body, you can see that there are sensors that are distributed throughout the body, and they're not uniformly distributed. In some locations, you have more sensors where they're needed. And so one might imagine that in a structure, to be able to detect damage, to be able to fully understand the state of the structure at arbitrary locations, that one would need to have such a dense array of sensors. And indeed, this is the Stonecutters Bridge, cable-stayed bridge in Hong Kong, and there are over 1,000 sensors on that bridge. So these are all cabled sensors, they're all wired, and we're moving in this direction as a community, but we're not there yet. And so the key to the development of the next generation of structural health monitoring systems, to be able to have the scalability, the cost savings, is going to be embedded computing and sensing. So the embedded computing and sensing has been oftentimes termed smart sensors, and these are a few of the early smart sensors. And one of the key features here, they all have onboard computational capabilities. They're wireless, battery-powered, they leverage technology, and relatively low cost. But they were also all proprietary. And so if one wanted to try and do some work in the arena of smart sensors, you had to start from scratch developing your own sensor boards, your own radios, A to Ds, etc. You had to assemble your sensor from scratch. So I had mentioned the DARPA NEST project, and this really changed things in the late 1990s whenever there were hardware platforms and software platforms that lowered the bar to entering into the smart sensing arena. This is one of the first motes, and it was designed for ultra-low power, ultra-low data throughput types of implementations. And indeed, there's a wealth of companies out there today that produce these smart sensors, and it's estimated to be $1 billion industry. So one might imagine that all you have to do is buy a bunch of these smart sensors and throw them on a structure, and then you're ready to go. You've got your wireless system. You can communicate with it. You don't have to worry about the cabling. They're relatively low cost, a few $100s each. You've got the processor, the storage, etc. But it's not that simple. There doesn't exist a good framework and a sensing platform that can support the demanding high data throughput applications such as structural health monitoring. Now, I do want to mention, though, this was a real milestone in bridge monitoring, the work of a student of Greg Fenvis's, Shamim Pakjad, and then I think David Culler's student, Kim. And they installed 60-some nodes on the Golden Gate Bridge to monitor it. And this is the implementation. And the basic idea was that they wanted to emulate a wired sensing network. And so you take your wireless sensors, and then you can harvest the data and then do the processing via centralized data acquisition paradigm. And so one of the things that I met Shamim over the summer, and one of the things he told me is that for one instance of sampling the response, it took 12 hours to get the data back to the base station, about 31 megabytes of data. And so what you can see is that while this was a milestone, we're not going to get to 1,000 sensors. It would be like sampling on one day and then waiting multiple days to get the data that you've sampled. So we've turned to a different platform than the Mica 2, which is what Pakjad and Kim used. And one of the key features of the iMote 2, which is the platform that we're using, it's an ARM processor, the Xscale PAX271, is that it's a user selectable clock speed from 13 to 416 megahertz. So it's got much faster processing capabilities than the Mica 2. So you can do onboard calculations. But maybe the most important thing is the available RAM. And so it's got 256K of available RAM on board and 32 meg external. So you can, with this processor, you've got the speed and you've got the storage to be able to do onboard processing of the vibration data. Now, for us, one of the questions is how good is this sensor in terms of transmitting data? We've seen people report 30 feet transmission distances with the onboard radio of the Mica 2 as well as on the iMote 2. And so we wanted to do before we adopted this platform, we wanted to do a thorough assessment of what type of performance we could expect. And the iMote 2 has a built-in gigaant. It's circled on the left figure. And then we also considered an external antenna on the right figure. We worked with Jennifer Bernhardt in electrical engineering at Illinois. She has an anechoic chamber, so we could understand the characteristics of the antenna. And what you see here is the red pattern. Now this is the copolarization, so this would assume that the receiving and transmitting antennas are parallel. The optimal situation is that the red interior here is the onboard antenna, and then the blue line on the outside is the external antenna. And so on the right is the cross-polarization graph. But what you see is that we get significant better performance out of the external antenna. That's not so surprising, but also we don't have very much directionality here. And so we didn't have to worry too much about how we placed the sensors as long as the antennas were parallel. But then we had the question of what does that translate into in the real world? And so this is something that it would be hard to find in the California area, but out in Illinois we've got big cornfields where there's no wires around, there's no Wi-Fi. And so we went out to one of those cornfields and we were able to test the ideal performance of the radio. And we used a loop-back test where we used reliable communication to make sure that we got the commands to the remote location, and then we turned off reliable communication so that we could understand the performance of the radio. And what you see here is this was just for 2 sensors. We had a fairly small sample. For the onboard antenna, which is at the top, you can see that at about 300 feet, 350 feet, we started to get a significant decline in the performance. And beyond that, because it's the digital transmission, it just completely died. With the external antenna, and these aren't on the same scale, what you see here is that we got about 900 to 1,200 feet transmission distance with that external antenna. And so this told us that we probably wanted to use the external antenna for our applications, and it would indeed meet the needs of our structural health monitoring application. But we also found that it was kind of flaky. And well, why is that? We got one of these spectrum analyzers so that we could look at the Wi-Fi frequency at this 802.11 frequency band. And here are the various channels. And what you see in here, this is whenever the iMote2 and the Wi-Fi network in our building were transmitting roughly on the same frequency. And it just swamps the iMote2 signal. We also found out that we've got a very old microwave in the laboratory, and everybody when someone turns it on, VPN drops on all the Wi-Fi signals, and you're not going to get any data. So by understanding this, then one can choose the channel for transmission for the iMote2 and get away from, or have less trouble with the internet, but the microwave is still problematic. We also wanted to see what's the effect of concrete walls, of brick walls, and we found that in comparing when the iMote2s were in line with each other as compared to if you put it behind a steel structure or reinforced concrete or concrete masonry infills, that we got very good performance. So you may have other issues, but the performance of the antenna was quite good. So this gave us confidence to use the iMote2. So then we went on to the next question of let's figure out what sensors we can use. And so as with many of the smart sensors, the sensor board is stackable. And so you have 2 options for using sensors on this one. The interface, it allows digital I/O only. And so there's no onboard A to D. And so you either can use the basic sensor board, which was created by Intel, or you can develop your own. Now, we started out using the basic sensor board because you say, well, if there's something already developed, why not use it? And we were shocked. This is the basic sensor board, the top and the bottom, and the features are it has a light sensor, temperature and relative humidity sensor, and it uses a triaxial accelerometer with an onboard A to D converter. And so you get a digital signal out that can be sent directly to the iMote2. The limitations, though, it has low ADC resolution, so you only have 12 bits. And this was one that just shocked us. They said that the sample rate was, you specified the nominal sample rate, user selectable, and plus or minus 10%. We thought this was maybe a 6 sigma bound. You know, how is it possible you could have a plus or minus 10% sampling rate on a sensor? But indeed, with this handful of sensors that we had, we saw a plus or minus 10% sampling rate. And so how can you use a sensor? You set it at 560 hertz or 280 hertz, and it's really sampling at 245 hertz. And so this was surprising to us. Another thing is that even within that, the jitter, the clock jitter, that is, we had variation in the sampling rate as a function of time. And so this basic sensor board, as it came, you could pick it up, you could shake it, everybody'd say, oh yeah, there's a signal on your screen. But it was useless for the purposes of structural health monitoring. In addition, for those of you that have taken data, aliasing is a problem that we all deal with. And so this system, it had a single pole anti-aliasing filter on it. Set it, it was user selectable depending upon what capacitor you put on there. But they said that the resistor was specified as plus or minus 20%. And you say, well, gee, that's a big range. And indeed, it was. There wasn't any way to measure it directly, but we, based on our experiments, we found out that they weren't joking. It was roughly plus or minus 20%. And so what happens is that you've got this filter. In this particular case, you can see that the cutoff is a little over 40 hertz for the particular nominal parameters chosen. And because you have this variation in the value of the resistor, then your anti-aliasing filter can have a significant variation in the gain, and the phase match can be even larger. So you can have a plus or minus 5-degree phase match at 40 hertz. And so again, the quality of your data is going to be useless. You can make some nice pictures, but it's not appropriate for engineering use. So now what I'd like to tell you about in the time that we have remaining is the framework that we developed at Illinois, which these are the various components of any sensor network. There's the sensor nodes, the network, and the algorithm. And so we've made some contributions in all of those areas. And then there's the system integration. So our efforts have been focused on using the iMote2, and we developed a new accelerometer board that I'd like to tell you about. We've developed some open source middleware services that we hope lowers the bar on using this platform. And then we've developed some new strategies for detecting damage that can be implemented in the distributed computing environment intrinsic to smart sensors. Let me first turn to the accelerometer. So this is what I showed you before. We designed a board. Jennifer Rice, one of my students, designed a sensor board. And it has 3 axes of acceleration, user-selectable anti-aliasing filters. So we can go from 10 hertz sampling up to 115 kilohertz sampling. And the aliasing is not a problem. Accurate clock and timing components. And here's the board in the top right. And the key is this 16-bit A to D converter, which is a quick filters chip. It samples at 12.5 megahertz. It has a 500 kilohertz anti-aliasing, and then it does digital filtering and decimation after that. It's relatively inexpensive, and then it directly dumps the output out for the iMote2. It's a 4-channel A to D converter, and so we can get high-quality measurements using this quick filters DSP chip and have the anti-aliasing filters built in. As a matter of fact, they give an FIR Filter Design tool, and this is the type of thing that we might design the anti-aliasing filter, an elliptic anti-aliasing filter. Here you can see you can determine what the roll-off is and what the ripple is in the filter, and then you download that directly to the chip, and then it's ready to run. This is just some testing of that accelerometer and compared to a wired reference accelerometer on this small shaking table. And what you see is the time domain, the frequency domain, the power spectrum, and then this is a transfer function between the 2 sensors. And it's very flat except below 1 hertz, and that's more a limitation of the shaking table than it was a limitation of the sensor. So this iMote2 combined with the SMA sensor board forms a good platform for us to do our work. The next thing I'd like to tell you about is the middleware services that we developed, and this was in partnership with the Open Systems Laboratory, Professor Gul Aga's group at Illinois. And middleware services, this is the glue that bridges the gap between the SHM application and then the operating system. We're using TinyOS in this application. And, whoops, I went backwards, sorry. So we've developed 3 classes of middleware services. The first is that we have to worry about efficient data and power management, and so we developed some model-based data aggregation approaches. One has to worry about data loss, and so we developed some reliable communication protocols. And then also high-quality synchronized data, and so we developed some synchronized sensing protocols. Because of time, I'm only going to tell you about the last one because it was also one of the most mysterious for us. So there's many synchronization protocols out there. In this particular case, we used a beacon approach where we could get synchronization to approximately 20 microseconds, very high synchronization. But what we found is that the clocks on those chips, they drifted on the accelerometer chips. And so we had to not only synchronize, but then get the offset and to create a linear reference, a linear mapping for the various clocks so that we could keep synchronization over a long enough period. You know, this is only 160 seconds, so it's not like it's over 2 days. And so this is an important issue. But after you do the synchronization, that doesn't get you synchronized sensing. And that may be somewhat of a surprise, but what we found is that when you have your, sometimes I do this, I say, okay, everybody, when I say go, raise your hand. And there's a distribution of when people raise your hands. And it's similar with the sensors. When you say start sensing, there's a microprocessor in there. It may be busy. If you open up Microsoft Word, sometimes it opens quickly, sometimes it doesn't. It depends on what the processor is doing. And so unless you shut down all the processes on the smart sensor except for sensing, you're going to have this variation. And you've got differences in sampling time also. And so if you took a bunch of sensors that should be generating the same signal, this is what you might get, a hodgepodge of responses. And is it possible to get those sensors to give the same response? So if you're measuring the same response, can you get it to give the same measured response? Or can we take those sensors and get them on a common time basis? And so Tomo Nagayama worked on this problem, and he developed a resampling strategy where you take and you upsample the signal by putting zeros on the axis. You then filter, and then you downsample. The problem is that if you have two signals that are very close to each other in sampling frequency or in their starting time, you have to do a huge upsampling to the megahertz range. And so this is not possible to directly implement this. Instead, we use this polyphase implementation in which we did linear interpolation in between the nodes so that we could get finer resolution. And this indeed provided the performance that we needed. And as a matter of fact, on the left here, these are some sensors that should have the same, they were on the same structure, receiving the same excitation, so they should have the same phase. If you look at the cross correlation, zooming it up here, there's roughly 1 degree at 100 hertz, or about 28 microseconds in phase difference. And so by using this resampling approach, we're able to get not only synchronized nodes, but synchronized sensing, which is critical for the application. So let me tell you about this distributed computing strategy. Typical approaches for structural health monitoring use centralized data acquisition, where all the information is brought into a central computer. And so this is not scalable to the large number of sensors that we expect. And the analogy that's good, this would be like everybody in the United States trying to talk to the president at the same time. Maybe you don't want to talk to the president, but it's still a good analogy. In contrast, there are people that have proposed an independent processing approach where each of the nodes, they don't talk to each other. And that's like in a society where everybody is their own doctor, their own lawyer, etc. And so this approach in particular, you lose spatial information about your structural system. So there's no information about mode shapes, although it is scalable. So the approach that we've advocated is a hierarchical approach in which there's collaboration among the various nodes in the structural system. And so this also has the analogy to our representative governing system. Now, we used what's called a damage locating vector approach to implement the damage detection strategy in a distributed manner. And I'm not going to go into great detail here other than just to give the basic idea. This F sub U on the left, this is the undamaged flexibility matrix that's been experimentally identified. Through continuous monitoring, then we can get an experimentally determined flexibility matrix of the damage structure. We then form determine a set of vectors L such that the displacement in the undamaged and the damaged structure is the same. And so that gives us a problem where we can find L in the null space of that difference matrix. Physically, what this says is that I'm looking for the load vectors that don't induce if there's no load in this damaged element, then the displacements before and after damage are going to be the same. So I'm looking for the set of load vectors which will induce no damage or no load in the damaged element. I then apply that to a analytical model of the structure, and I look for those elements which have low stress, and that gives me the candidate damage location. Yung Gao took this idea, which was originally put forth for global using the centralized data acquisition system, and he said, well, I wonder if we looked at a bridge structure as shown here, and I only monitor the elements in a particular region. And element 5 was damaged, and you can see this damage index that's shown here indicates that element 5 is indeed damaged. We then go on to the, and so this shows us that. We then go on to the next group of sensors, and we find that it shows that the damage indices don't indicate a damaged element, and indeed that's the case in the remainder of the structure, and there is no damage in those others. So this gave us the hope of being able to use this localized damage detection. This is the implementation in an experiment of the autonomous operation. For those nodes as shown here, this would be the first group, and the node indicated with the 1 is the cluster head. That's the leader for that group. This is group 2, and this is group 3. So only nodes 1, 2, and 3 communicate with each other. Within the communities, there's model-based data aggregation takes place. Damage detection is implemented using the stochastic damage locating vector method. And then the cluster heads communicate with each other to compare, hey, I found an element in my group that was damaged. Did you find that element was damaged? And if it's consistent, then the information is reported back to the base station. If it's not consistent, then damage or the data is retaken. This is a test structure in our laboratory, and you can see the iMote2 mounted there. And we also mounted some reference sensors to keep us honest so that we could see if the data we were collecting with the wireless sensors was of adequate quality. And what we found is that indeed, in this particular case, we had element number 8 was damaged, as shown here. And indeed, element number 8 was in 2 of the groups, groups 1 and 2, and it was identified as being damaged in both cases. So the efficacy of this approach has been experimentally verified. Now, let me just say that Tomo Nagayama worked on this for a couple of years, and when he left last year, we had to retool. The code that he wrote, it was about 1.8 megabytes, 207 files, 50-some thousand lines of code. And for another student to dig in and use any of that is a virtual impossible task. So it works, but it was just almost of little use. So what we did was we worked with our computer science department, Gualaga, to develop a service-based architecture and what we call a structural health monitoring services toolkit. And so it's written that, this is interesting. This just shows where we came and where we are. First is where we were. The time frame for writing a program on the iMote2 was years, basically a PhD dissertation. With the toolkit we've developed, it's still a class project, 1 to 2 years, and we're moving towards this macro programming environment where you can program on the network in a matter of minutes. Now, we're at this level, and that services toolkit, the contents of it, there are foundation services such as the universal sensing time synchronization, reliable communications, and a numerical library. There's application services, including correlation function estimation, eigensystem realization, etc. And then there are test applications and tools and utilities that are available. So the basic idea under here in this service-oriented approach is that the services, if here is our application that we wish to develop, is that the foundation services provide the basic capabilities. The numerical services, you can implement your algorithm, and then your application services are on top of that to make your application. And then, as I mentioned, Kirill Mechatov, his efforts in computer science, and they're using the structural health monitoring as the test bed, is to develop a wireless sensing network macro programming in which one programs the entire network as opposed to node by node. So we're not there yet, but that's the direction that we're heading. In the couple of minutes that we have remaining, I want to just tell you about some full-scale applications that are on the horizon and close the talk. This is a historical bridge built in 1912, about 8 miles from Champaign. You can see it's 2 spans. It's over the Mahomet River, the Sangamon River in Mahomet. And so it used to be a traffic bridge, but now it's a pedestrian bridge, and so it's very good for a test bed. It serves as a full-scale bridge prototyping for other applications. Here's just a picture of the bridge in the various seasons. And you can see it's been quite worn over the years. This is some of the pitting corrosion that is seen. There's also some section loss. There's local buckling. There's bent elements. And then there's, you can see where it's been damaged up here, completely corroded away, and then they've welded in some supports. So the thing that we can do with this bridge is we've got 2 identical spans. We can't damage it. Couldn't get damaged much more anyway, but we can't damage it, but we can compare the 2 spans. One is being damaged, the other undamaged, and look for anomalies between the 2. This is where we installed the base station underneath the center pier. That base station, it has the ability to communicate with the wireless sensors. It also has the CDMA cellular connection and then a Wi-Fi connection. Here are some of the sensors that are being mounted on the bridge. They're in those small boxes. And here you can see what's inside the box. It's basically we're using D-cell batteries, and then there's the iMote2, the battery board, and the sensor board. And there they are mounted on the structure. And here is some data that we collected from the sensors, from the triaxial accelerometer, due to the typical jump test that one uses in these types of structures. This is a precursor for the Jindo bridge. We are working with KAIST to install 70 sensors on this bridge during the coming year. This is another bridge in South Korea that we'll be working on next year, a bridge in China, and one in Japan. So we have quite a few full-scale implementations that are in the future. So in conclusion, the needs for structural health monitoring systems for civil infrastructure increases very rapidly in industrialized nations. And it's very exciting because it allows us to better understand our physical world. What I hope to have shown you is that there's an open source smart sensing framework that one can pick up and run with in various applications, and that full-scale validation is underway. This is the website where the various reports from this work, as well as the software, is available. And so if you have interest, I hope you visit there and also contribute to the software base. Thank you very much.
Thank you very much for the talk, Bill. In the spirit of the CITRIS Nokia Distinguished Lecture on Cyber Physical Systems, we'll give you the plaque of the lectures, and we'll have a couple minutes for questions.
What was the GPS rover station, and what sort of a sensor do you use for corrosion?
The sensor in this particular case, we're not monitoring corrosion directly. Corrosion is a form of linear damage, and so we're looking at the changes in the dynamic behavior of the structure as an indication of where such damage may have occurred. There are other people that are looking for more direct measures of corrosion damage, but that hasn't been the focus of this work.
And the GPS rover station?
We don't have a GPS on rover station on this system. Is there one in particular that you...
I don't know what it is. You had it on a couple slides.
Oh, I'm sorry. I'm sorry, from back there. That's just a particular GPS system that they put on that building so that they could measure the displacement of the building. So nothing very special.
Bill, very, very informative, very interesting talk. What are the prospects for localizing damage, say, in a real structure with partitions, reinforced concrete, furniture, ceilings, and so on?
That's a very good question. I think from global measurements, the possibility of localizing damage in such a system is very small. One has to have, as I was indicating there, a dense array of sensors, and you also have to have a good understanding of the structure. What type of damage mechanisms are you expecting, and then different types of sensors need to be considered. In our particular case, we have a sensor board that's being developed right now that'll have a strain sensor on it. It'll have temperature, humidity, light, 3 axes of acceleration, and then strain. So you'll have both local measurements as well as these global responses that you can put into your damage detection strategies. But it's a structure by structure type of thing, and the focus right now for most people is on the signature bridges. But what we imagine is that in the future, rather than taking a few bridges and then putting a lot of sensors on them, that it may be that we take many bridges and then we put a few sensors on it, monitor it for a couple of days, extract the information, and that can be a supplement to the current inspection strategies that FHWA is using. As a matter of fact, FHWA recently established the long-term bridge performance program, and it's to try and understand what we can do in this context with monitoring to help them better manage their bridge inventory.
So for wireless smart sensors all over a bridge, are you considering the design of security implications?
We are. We haven't taken that to the level of where it's been implemented yet. Now that we actually have a bridge and we've got sensors on it, then we've started to think past just getting things working. And so that's a class project for 2 of Professor Aga's students in their embedded systems course. And so that's where we're heading. They're looking at biological emulation of immune systems to try and develop a security system. So I don't know exactly where we'll go with that.
Do we have any other questions? Okay, so please join me in thanking our speaker again.